Hi everyone, welcome back to my videos. I'd like to do a short problem supplement based off of the last video I did on circles. So I'm just going to go over two problems. They're quite challenging, so if you don't want to watch this video, that's fine. If you do, that's great. I'm just going to be solving two problems here based off of chords. So the first problem is, given a circle with diameter BC, segment AC is parallel to segment BD. Prove that segment BD is congruent to segment CA. So we start off with what we know, and we know if a transversal intersects two coplanar parallel lines, then alternate interior angles are congruent. So we're given that segment AC is parallel to segment BD. If we extend the segment, we get line AC and line BD, right? So if we take BC, the segment, as the transversal, then angle C and angle B are alternate interior angles, right? Because they're in the interior region bounded by the parallel lines, and they're on opposite sides of the transversal. So what I'm going to do next is I'm going to draw the perpendicular bisector to segment BD, and we'll call M the point of bisection, right? And I'll do the same thing to segment AC. I'll draw the perpendicular bisector here. So we'll only consider just the segment MO, which is technically the subset of the entire perpendicular bisector. And the reason we can do that is because through an outside point, that means a point that's not on a segment, exactly one perpendicular can be drawn to a segment, right? So we know that a perpendicular bisector to a chord passes through the center of the circle, right? That's one of the theorems we showed in the last video. So the perpendicular bisector to segment BD passes through the origin. I'm going to call the segment MO the part of the perpendicular bisector between point M and point O. And then I'll call segment NO the part of the perpendicular bisector that passes through the origin, right, to segment AC. Now, we know that perpendicular lines meet at right angles, so angle OMB and angle ONC are right angles. So this angle and this angle are both right angles. And we know that all right angles are congruent, so angle OMB is congruent to angle ONC. We know that segment OB is congruent to segment OC because all radii of the same circle are congruent, right? Point B and point C are points on the circle, and point O is the center, so segment OB and segment OC by definition are radii, right? Using the angle side postulate with what's in 3, what's in 9, and what's in 10, we get that triangle OBM is congruent to triangle OCN. By corresponding parts of congruent triangles are congruent, segment BM is congruent to segment CN. We can use the fact that we're dealing with a perpendicular bisector, right? So BM is, the length of BM is going to be what? Half of BD, right? And the length of CN is going to be 1/2 of the length of AC, right? Because to bisect is to split into two congruent parts, right? So if I multiply both sides by 2, the congruence relation in statement 12, and then I substitute, I get segment BD is congruent to segment CA by substitution. Okay, and this is the other problem I want to go over. So this is also a challenging problem. So given triangle ABC is isosceles, segment AM is an altitude of the triangle. Circle P has radius OB. So this is the radius right here, OB. And we're given that length of AB equals L, length of AM equals H, and length of OB equals R. Find R in terms of L and H. So we write down what we know, and we know all radii of a circle are congruent. So segment OB is congruent to segment OA, right? OA is also a radius because A is on point on the circle, and O is the center of the circle. So if you draw a segment, we get a radius, right? So I'm going to use the definition of segment congruence and substitution. So length of OB equals length of OA, and we know that length of OB is equal to R, so length of OA is also equal to R, right? I can use the betweenness property of segments to get MO, length of MO plus length of OA equals length of MA. Do some algebra, we get length of MO equals length of MA minus length of OA. And then I'm going to substitute what I have in 4 into the equation I have in 8. So length of M8, so we'll get H, and then we'll get R. So length of MO is equal to H minus R. We know that angle 1 is a right angle because an altitude is perpendicular to the side to which it is drawn. I can use the Pythagorean theorem to triangle AMB to get BM squared plus AM squared equals AB squared. I'll do some algebra. BM is equal to the square root of AB squared minus AM squared. I'll substitute what I have in statement 4 into statement 12. I get BM is equal to the square root of L squared minus H squared. Next, I'm going to apply the Pythagorean theorem to triangle OMB, so the smaller triangle here. And we get BM squared plus MO squared is equal to OB squared. And then I'm going to substitute what BM is. BM squared is the square root of L squared minus H squared squared. So squaring the square root cancels it. So you're left with L squared minus H squared. And MO, we know in statement 9 that MO is equal to H minus R. So MO squared is going to be H minus R squared. I'll do some algebra here and solve for R, right? The R squares cancel, and so we're left, also the H squares will cancel, so we're left with, something we can solve for in terms of R. So R equals L squared divided by 2 times H by algebra. So that's all I have for you in this supplement. So it was just 2 problems. I thought they were good problems to go over. This video is totally optional for you to watch it. If you feel like you got enough information out of my last video, that's great. And that's all I have for you tonight. So I look forward to seeing you during my next video. All right, take care, everyone. Bye.